Hello and welcome to Physics 262 Pre-Lecture Notes. I'm Dr. Steve Brule. In today's lesson we're going to cover two chapters, just parts of two chapters. We'll learn the definition of electrical current. We'll discover that Ohm's law says that resistance is defined as the ratio of voltage to current in a circuit or in a circuit element. We'll use a cool circuit simulation program to show that current is the same for resistors in series and voltage is the same for resistors in parallel. We'll derive the formulas for resistance and parallel resistors in series and parallel. Alright, we got it. And we'll study a complex circuit with both series and parallel components. And finally, we'll look at the difference between AC and DC current. Well, let's look at how we define current. Current is defined as the charge that passes some point divided by the time it takes that charge to pass that point. So if we have, and we usually talk about positive current flow, even though we know really electrons are flowing in electrical circuits, we pretend that we're considering positive current flow. So if we have 1 coulomb of charge that passes some point in 1 second, that's the same thing as 1 ampere. 1 amp of current is 1 coulomb per second. Those old CRT computer screens had an electric current hitting the inside of the screen from the back of the screen. There was a cathode ray tube shooting electrons, and it shot 200 microcoulombs every second towards the screen. Let's work a little problem. If we have a computer chip that draws 150 milliamps of current, how much charge flows through the chip in an hour? I think we might have worked this at the beginning of the course. So I equals Q over T, so we could say that the charge that flows past some point is equal to the current times the time. So the current is 0.150 amps, that's 150 milliamps, times the time is 3,600 seconds, and then you get, I'll go ahead and do that for you real quick. 0.15 times 3,600, 540 coulombs. Right, what else do we have here? Well, most materials obey what's called Ohm's law, and what that means is, like here we have a resistor that's 3 ohms, and you don't know what that is yet, but you will in a second. So here's just some object that has a resistance of 3 ohms, and we see that as we increase the voltage on that object, and this is somebody who did this experiment. They had one battery and they got, looks like about 0.19 amps. Then they had 2 batteries and they got about 0.5 amps. So then what the idea is that as they increase the voltage on this resistor, the amount of current that they observed increased proportionately. And then instead of having 1 resistor, they did the experiment again with 2 resistors, so it had twice as much resistance. And then as they increased from 1 battery to 2 batteries to 3 batteries, the amount of current went up, and it was a linear relationship. So it's that linear relationship that defines what Ohm's law is. Now, all materials do not obey Ohm's law. In particular, semiconductors don't obey Ohm's law. If they did, we'd be in trouble because we couldn't amplify things. Another thing that doesn't obey Ohm's law is a light bulb. Later in the show we're going to use light bulbs as if they did, but I'll just mention right now that you can see that as they increase the voltage on their light bulb, the amount of current that they got through the light bulb did not increase linearly. So what happens is as the filament of a light bulb gets hot, the resistance to current flow goes up. But we're going to disregard that for the rest of this show. So don't even think about that when we use these light bulbs later, or even when you're doing your light bulb lab in 262 if you do that. I think they actually do measure the how the resistance changes in a light bulb in that lab. Okay, anyway, a car headlight draws about 4.5 amps of current when it's connected to a 12-volt car battery. The battery in a car is 12 volts. You should know that. So we can calculate the resistance. Resistance is defined as the ratio of voltage to current. This is essentially what Ohm's law says. So that Ohm's law, you probably know, is V equals IR. So if we solve for resistance, and we see how resistance is defined, it's the ratio of the voltage you put across some element divided by the current that you observe going through it. And for that particular light bulb that had a 12 volts applied that drew 4.5 amps, there were 2.7 volts per amp, but what we call that volts per amp unit is 1 ohm. That's 1 ohm of resistance. Well, resistance in an electric circuit is analogous to a constriction in a pipe that carries water. So here's a pipe carrying water, and you see there's this constriction in the pipe. Well, that's going to limit the flow of water. It's going to make a kink in the pipe, and it makes it harder for the water to flow. So a resistor is sort of like a kink in the wire, even though it's not physically a kink, but it's something that offers resistance to the flow of electrons in a circuit. So in the same analogy, the battery is like a pump. So the pump is pumping water through a circuit, and maybe there's a constriction in the circuit here, the water pipe circuit, and that would be like a resistor. So the battery's like the pump. Well, I'm just throwing this in. You might wonder why that birds, when they land on high voltage power lines that are not insulated, why don't they get electrocuted? Because these voltages, it might be 100,000 volts that they're sitting right on. So you might think, well, here's this bird way up at 100,000 volts. Wouldn't that kill a bird? But the thing is, let's look at that picture at the very beginning of the show. See, here's this bird, and you see that this wire is not insulated. There's no coating around that wire. So the bird's feet are right on the wire, so you think, well, why doesn't the bird get electrocuted? And the reason is because for an object or a person or a bird to get electrocuted, current has to flow through their body. Well, the feet of the bird are at the same voltage. So there's no reason why the current would go through the bird. So the only time when you get current through the bird is if it took 1 foot off of the wire and maybe touched the pole, so where the pole is at a 0 volts, and now we have a voltage drop across the bird, and then you'd get current flowing through the bird, and then it would be electrocuted. So that's how you get electrocuted, is when you have a voltage drop across your body. It's okay to be at a very high voltage. And I wish I had a picture of I didn't think of this, but the workmen they actually work on these power lines while they are live, carrying current, and the workman just hooks onto the wire with a metal, wire himself. It's just got a hook there, and then he becomes, or she gets up to the same potential, and then as long as they don't touch the ground, they don't get electrocuted, just like the bird. Okay, let's get back to the show here. Okay, so we're going to spend the rest of our show today just looking at some electrical circuits using this neat little program that simulates electrical circuits. So let's go into that program and create this particular circuit. So 3 light bulbs, a switch, and a battery. So let's see if I can switch the programs here. Sorry about that, I'm going a little slow here. Where does it say switch programs? There we are. So I'll go into here. I'm going to get I'm going to reset all. And for this first one, I'm going to build it so you can see how easy it is to build it. So I'm going to take 3 light bulbs, and then I'm going to get a battery. Where's my battery? There it is. And by default, that really looks just like a regular battery, like a AA battery. And a AA battery is 1.5 volts, but the default for this is 9 volts. And we'll just leave it at that because that's what I did in the previous thing. Let me get rid of the voltmeter for now. Okay, so let's connect things with wires. I don't want to connect those points. I want to connect this to this. There's two. Did you know that there were two connection points on a light bulb? That's what allows the current to flow through the filament here. We did something with that in the very beginning of the course, remember? So here's a wire. I'm going to take another. I could just jump down there, but I want to make it sort of nice and clean looking. So here we go. I'll connect that wire to the battery. I'm going to put a little switch on it so I can turn the circuit on and off. And I'll put another wire over here. Take another wire. Get another wire. Put this over to here. I'll just put that over onto that. Okay, it doesn't look as nice. Okay, so now I'm going to close the switch and watch how. Why doesn't it go? There it goes. Watch how the current flows through the circuit. So you can see that all these little balls illustrate electrons flowing from the negative terminal to the positive terminal, and they flow in one side of the light bulb through the filament, and then they come out this side of the light bulb, come in here, hit that part of the light bulb that's connected to that part of the filament, come through, come out the bottom, hit the side, go through the filament, come out the bottom, and then they go back through the switch and eventually back into the battery. So it's a closed circuit. I can open the circuit by opening that switch and everything stops. Watch this. I'll turn the voltage up higher. We had it at 9. Let's put it at 100 and we'll really see the... see, nothing flows until I close the switch. Now, look how much light is coming out of those light bulbs. Those electrons are really moving now. Uh-oh. Don't want to overload the thing here. Let's turn that off. Okay, I'm going to go back to 9 volts because that's what I worked all of our problems previously with. Okay, so let's go back to the PowerPoint and see what we're supposed to be doing. All right. Well, the thing that we discovered in that little simulation is that the current, when these three elements are in series, and what defines what a series circuit is that the current through one element is the same as the current through this element. So if the current that goes through one thing is the same as the current that goes through the other one, they're in series. Or if we use the little bug model that we used with capacitors, if you're at this battery and you're this bug taking a trip, and if you go through one of the elements and the only way to get home is to go through this door and then through that door, then all those doors are in series. If there's another door, say if there was another light bulb here, went like that, then these light bulbs are not in series with that light bulb, or that light bulb is not in series with that light bulb. You can say these two are in series together, but they're not in series with that initial one because the current through, here was the other one here, and there's our alternative path. So the, let me get a different color. So if there are two paths for the current to go through here, then the same current is not going through these guys that went through this. These guys are getting less of the current because it branched out. That's one of Kirchhoff's laws that says that the he says the sum of the currents at a node is 0. And what that means is an easier way to state that. A node is a place where the current can branch off. And what he's saying is that the current that goes in there equals the current that goes out. So here we've got some current coming in, some comes out here, some comes out there. So if this was 3 amps and this was 2, guess how much this one would be? 1. All right, that's all that Kirchhoff's current rule says. So the sum of the voltage drop across each light bulb must equal the battery voltage. That's another one of Kirchhoff's laws, and I didn't spend a lot of time with that in this class because it's so simple that you use it and you almost don't even have to say that you're using it. So if you have a battery that's 9 volts, so you go, what Kirchhoff's law would say is that if you go up 9 volts in a circuit, and then you have to drop 9 volts. So if you went plus 9 volts through your battery, that increases your voltage, then you're going to drop voltage across each element in the circuit, and eventually if you draw a loop in the circuit, you have to get back to 0. So if we start at 0 volts, we jump up to 9 volts because of the battery, then we're going to drop down to 0 volts again at this point. And since you can argue by symmetry here that since each one of these light bulbs has the same resistance, they should all have the same voltage as well. So you could see that each one's going to have a 3-volt drop across it if we have a plus 9 volt here. So if we go up 9 volts on our battery, we're going to go down 3 here, down 3 here, down 3, and we'll get back to 0. That's Kirchhoff's loop rule. All right, well, so we just wrote Kirchhoff's loop rule that said that the sum of the voltages in a loop is equal to the battery that's how we're writing it. Okay, so then V1 is equal to I1R1. That's Ohm's law. Ohm's law says V equals IR, and we can write V1 equals I1R1, or V2 equals I2R2, or V3 equals I3R3. Well, as we saw in that little demonstration, the current, why did that do that? The current that comes through one of the elements is the same as the current that goes through the other two elements, which is the same as the current that the battery put out. So let me go back to red here. So I would call this I, if this was 1, 2, 3, this is I, 1, 2, 3, that's the total current. And then the current through this guy is I3, the current through that one is I2, this is I1, and I can see that I1 is equal to I2 is equal to I3 is equal to I1, 2, 3 because the current in a series circuit is the same through every element. If that current is not the same current, those elements are not in series. You can write that down. Okay, so then we're going to factor that current out of this equation, and then it's just the same as I 1, 2, 3 times the sum of all the resistances. And what we've just done is we've derived the effective resistance of 3 resistors that are in series. So when you have resistors in series, you just add up the resistances and you get the total resistance. So R total is equal to R1 plus R2 plus ... That's the law for adding resistors in series. It's the opposite way that we do things with capacitors. Well, let's find the voltage drop across that first bulb. I think that was 1, wasn't it? And that's 2, and that's 3. So first of all, we look at this circuit and we say the equivalent resistance of those 3 elements in series is just the sum of each one of the resistors. And since each one had a resistance of 10, you didn't know that, but that's what the program did. So then the total resistance is 30 ohms. So then I can say the total current, and this is what you'll do in every one of these problems. The first thing you do is reduce a complex circuit into a simple 1 resistor, and 1 equivalent resistance, and then you find the total current, which is the current that's being put out by the battery. So that's voltage over resistance by Ohm's law, and that our battery was 9 volts divided by our total resistance, which was 30 ohms, so we get 0.3 amps. It should be coming out of this guy. Well, we know that in a series circuit, the current through every element is the same as the total current that's put out by the battery. So then I can say that I1 is equal to the total current, which was that, so that when I write Ohm's law, see how I'm using those subscripts? V1 equals I1 R1. So there's the first current, or I through element 1 is 0.3 amps, which is the same as the total current in the series. There's the resistance of R1, and I have a voltage drop of 3 volts, and that's what we thought it ought to be. And okay, so we can test the voltage across elements in a circuit by using a voltmeter. And let's jump over here into our circuit and we'll see how that works. So let's see here. I go to switch programs and go to in here. Okay, so here's the a voltmeter, and here's a battery. The positive end of the battery, here's a switch. Let me open the switch. So that stops the current flow. So this is positive over here, this is negative. So they have these little balls moving through the circuit, and those are the electrons that are moving. So if we put our negative lead of our voltmeter at the negative terminal of the battery, we're going to just assume that, well, we'll kind of say that's our ground point or our 0 point. So if I put over here right now, it's measuring 0 volts, but once I close the switch, we've got 9 volts. Okay, so now I'm measuring the voltage of the battery across here, and if I go to here, I'm at 0 volts. So this is going to be 0 all along here, and then as soon as I go over to here, I've got 3 volts. And then if I go over to here, I'm going to be up to 6 volts because the voltage drop across each battery, each light bulb is 3 volts. If I put my other terminal here, then I'm getting the voltage drop across light bulb 2. And if I get here, I'm getting the voltage drop across light bulb 3. Or no, that's 1, isn't it? So then if I do this, I'm getting the voltage drop across all 3 light bulbs. So the thing about a voltmeter is that you put it in parallel with whatever element that you're measuring, and then you'll get the voltage drop across that element. Now let's get rid of our voltmeter and stick an ammeter in. Now for an ammeter, I have to break the circuit. Now no current is flowing, and then I'll take my ammeter and stick it in here. So let's see, there it is. So now for an ammeter, you have to put that in series with whatever element you're trying to measure the current through, because ammeters have to be in series. Because in a series circuit, the current through the elements are the same. So I want to get the same current through my ammeter as through my light bulb there. Let's see, am I actually getting, I think that it didn't quite, yeah, it hooked on to the wrong point. Let me split the junction, because I got the wrong, if you were paying attention, you saw that that was not the right. Now what did I do? Let me split this junction. Okay, so the thing is, let me move this over here. This is why I work things out before I do the video. Alright, so let's put the light bulb there. Okay, so now it's connected to the bottom of that part of the light bulb. And before I had my ammeter connected to the same point, that the bottom point of the light bulb. And then, so we were essentially bypassing the current through there. But now I'm going to connect it to the right place, and we're getting 0.3 amps like we're supposed to get. So that's how you measure the current in a circuit. You have to put the ammeter in series with the elements. Let's return to our show. Okay. So I already did that. Oh, I just wanted to show that if you wanted to have more voltage, we could double the battery. You put batteries in series, and then the voltage for each battery would be, you just add the voltages that in this circuit if they're in series. Sometimes you'll have batteries that you put in parallel. Why would you want to do that? Why would you want, let's say, 3 batteries and connect the same ends across here and around the bottom? The reason you do that is, even though each battery is the same voltage, a battery only has the ability to produce so much current before it starts sagging its output voltage. So then if you need to have a lot of current, you might put a whole bunch of batteries in parallel, and the voltage would be the same for that parallel combination of batteries, but you would have the capacity to deliver more current. Alright, now let's calculate how much current flows in this circuit of 3 parallel light bulbs. The first thing you should notice is, just like with capacitors, we're going to look for these little sub-networks. So I see that those 3 I wanted to say capacitors. Those 3 light bulbs are in parallel. And from Kirchhoff's loop rule, the node rule, we know that the current that goes into one node, let's say this is a node right here. So if you had, we're calling that I1, 2, 3 coming in, well, coming out is I1, here's I2, and I3 is coming out there, 1, 2, there's I3. So I can say that I1, 2, 3 is equal to the sum of these 3 currents, because the battery's putting out a current of I1, 2, 3. That's the total current, but then that current is getting split up into those 3 paths, 1, 2, and 3. So I can make that equation. Then I apply Ohm's law to each one of these currents. Remember, Ohm's law is V equals IR, so if I solve for I, it's V over R. So I can say I1 is equal to V1 over R1, I2 is V2 over R2, etc. And then since each one of these things is in parallel, they're all seeing the same voltage. You look at both sides of each element, and they're all touching, so then that means that the voltage that each one of them sees is this battery voltage, this V1, 2, 3. I'm going to factor that out, and then I get just 1 over all the resistors like that. Plug numbers in, and I find that I should have 2.7 amps coming through the circuit when I turn that switch on. When I close that switch, I should end up with 2.7 amps. Let's see if that's what we get. Sure enough. I went ahead and did that ahead of time, so we didn't have to do it again. So there's 2.7 amps coming out of the battery, and then this would be I1 here, this is I2, this is I3. Alright, but what's important about this derivation right here is I can divide both sides by that quantity, and I end up with V equals I times, this is the equivalent resistance. So that's the equivalent resistance of a parallel combination of resistors. Better write that down in your notes. It's the opposite of how capacitors work. Well, let's jump to a little more difficult problem. Here we have a circuit that's complex because it has more, it's not just simple series or simple parallel. I've got a switch here right now that's off, it's open, and it's not allowing current to flow. I've got this switch right here that's closed, so it's just acting like a wire there. We're going to open that later and see what happens. But at the beginning, we're just going to do some calculations for this circuit with that switch closed. Okay, so the first thing you notice is that these 3 light bulbs, we're just considering them as if they were resistors. They're in parallel, so I can calculate the parallel combination of those 3 using the equivalent resistance of a parallel combination. That's 3.33 when I plug the numbers in. And then instead of this combination, I redraw the circuit with my R2, 3, 4 substituted in place of those 3 resistors, of where I broke the circuit. So here it was broken here and here. So then between those 2 points in the circuit, I replaced that with an equivalent resistance, which I calculated here. All right. What's our next step? We see that these 2 resistors are in series. The current going through this resistor has to be the same as the current going through that resistor. They're in series. So then I use my equation for calculating the resistance of series resistors. It's just the sum of those 2. So R1, 2, 3, 4. See how I'm using those subscripts? That's nice, isn't it? That's just the sum of those 2 resistors. I had a 10 plus that one was 3.33. That was the equivalent resistance of the 2, 3, 4. So I end up with 13.33 ohms for my total resistance. What do you think we'll do next? Every time you get a circuit, and then you simplify it until you just get to 1 resistor, and then you calculate the current through that 1 resistor using Ohm's law. So that's current is voltage over resistance. See, I keep track of my subscripts there so I don't get confused. So there's my total voltage Here's my total resistance, and I end up with 0.675 amps. Well, unfortunately, I checked that to make sure that that was right in our circuit, and that program that we have does not round up. It should say 0.675, and it just truncates and gave us to the nearest hundredth. Well, we'll live with it. All right. So what are we going to do next? So now we ultimately want to, what did we ultimately want to find anyway? Let's calculate the total current in this complex. Okay, so we've already calculated the total current, but now let's find the voltage on this element right here. So we got down to this point. So now we're going to start going backwards. We note that the current through this element is the same. To go from here to here, we had simplified with a series circuit to a simple one resistor circuit. So if it's series, we know the current through each element is the same. So I just wrote that out just to make sure I know what I'm doing. So that current is going to be the same as the current that I just calculated here. So now I can calculate V1 is just going to be I1 R1. Well, I1 was this 0.675. R1 was it was a 10 ohm light bulb. So I ended up with 6.75 volts. Let's check that. Sure enough, 6.75 when I put my leads across that one light bulb. Well, let's calculate the voltage on R234. So V234 will equal I234 times R234. So, and the current is the same through each one of those elements. It's 0.675 because they're in series. And then the resistance R234 was 3.33. Stuck that in there. So we should have 2.25 volts across the equivalent resistance of those three here. So I put my leads on either side. I could have put my leads here and here. That would have been, I guess, a little bit better conceptually so you could see. But this point, any point you put along that's connected with a wire is going to have the same potential. So I could put my lead anywhere along there, and I could put my left or my right lead anywhere along here. And I would be measuring the same voltage that's across each one of those. That could, because the total voltage across that equivalent combination of parallel resistors is the same as the voltage across each element. So 2.25, and is that what we calculated? Yes. Okay, and then finally I end this thing right here with, what did I do? I2. Oh, let's calculate the current going through one of these light bulbs. Since the light bulbs are all the same resistance, the current will be the same. But in general, the resistors that you have in parallel could have different resistances, so they would all have different amounts of current. So I found I2 using the same Ohm's law. I2 is V2 over R2. So V2, there's V2, we just calculated that. R2 was 10 ohms because each one of them had 10 ohms. So I would expect 0.225 amps to be flowing through this light bulb. And since each light bulb is the same resistance, that same current will flow through each one. So then I put ammeters in, and here was our total current, that 0.675 it should have been. And then that 0.675 branches off to 0.22. It should have been 0.225 here, which it's just truncating. And then this is 0.225, and this is 0.225. And if you add up 3 times 0.225, you end up with 0.675. So that's the current that comes out of the battery has to branch into these 3 elements that are in parallel. So the sum of all these 3 currents is equal to the total current that I had. It's neat. That's Kirchhoff's node rule for current. What voltage will be across R1 if this switch is opened? Why don't you press pause and think about that? Okay, we're back now. We know that we had a 9-volt battery here, even though these batteries look like they're double A's, which should be 1.5 volts. We're calling it 9 volts because we could adjust it in the program, and that's how it was. All right. So if we open this circuit, then that means that no current can flow into this from here. Well, if no current can flow out, no current can flow in either. So that means essentially we've just taken out that whole part of the circuit. And now we just have these 2 light bulbs that are in series. So we have 2 10-ohm light bulbs. My ohm there was not so good. I'm trying to go fast. Okay, so if you have 2 10-ohm resistors in series across a 9-volt battery, you could work that out, and you'd see that the equivalent R12 would be 20 ohms, and you'd find out the current that you'd get. Well, it's so easy. I'll just do it. Is V over R. So that would be 9 over 20. So our current should be 0.45. So there's 0.45 amps going through this part of the circuit right here. And since that same current flows through each one of those light bulbs, I can say that the voltage across one of the light bulbs is equal to V equals I through the 1 times R through the 1. So the current is going to be the same for both of them, 0.45 amps times the resistance, which is 10 ohms, and we end up with 4.5 volts. Wasn't that fun? Let's check it. 4.5 volts and at 0.45 amps coming out of that when that switch was open. No current is flowing in there. And if, let's see, maybe we can jump to that simulation and illustrate how that works. No, let's see if I can load that. Complex circuit with I meters. There it is. Okay, so there it is. So when I close this switch, now each one of the elements are getting, each one of the light bulbs is getting 0.225 amps through it, and we've got 0.67 amps drawn from the battery. But I open this switch right here. Wait a second, I'll open it. And then these two instantly drop to 0, and then because no current can, if no current can come out of that loop with those 2 parallel light bulbs, no current can go into it, so all the current has to go through here, and we had to recalculate the current, and it was 0.45. It was neat, wasn't it? Let's go back to the show. There it is. Oh, let's take a look how current flows in an AC circuit. So this is the last thing that I'm going to show you, and we're not going to do any AC problems in this whole course, but I do want to show you what AC current looks like, so because it comes up a lot. So let's look at this complex AC circuit that I already made. There it is. So this is an AC volt. See, you can have a AC voltage generator, not just a DC battery. And with AC current, see how the electrons move one way, then they move the other way, and when they stop, the light bulbs all turn off. And that's what's happening with our normal light bulbs, except, I don't know, that's an interesting question. I think there's still, even though there's a point where there's no current flowing right here, and there's no, and it shows no light, but it doesn't, it's only a fraction of a second, and I don't think that's enough time for that filament in that light bulb to cool down and stop producing producing light. The reason why a light bulb produces light is because the filament is hot, and as long as the filament stays hot, then it is always going to produce light. So if the filament cooled down the same as fast as the current is stopping, then the light would be flashing on and off. But since an incandescent light has some, you'd say, what do you call that? Sort of like inertia. It takes a while for it to cool off, so it's not going to go down to 0. Fluorescent lights are different, though. Okay, so did we get that? We can turn up the AC frequency. Let's turn up the voltage. well, it's already up to 72. Let's go up to 95 volts. So that means that see, it's just really shoving them through there. Let's make the frequency higher. So right now it's doing it at 0.5 hertz. Let's go up to 2 hertz. See how the electrons are sloshing back and forth at a faster rate. So AC is alternating current. It's going both directions, and it has a frequency. All right. Let's see what we've got here in our to end our show. What did we learn? Ohm's law is cool. We found out that current is the same for resistors in series, and voltage is the same for resistors in parallel. Kirchhoff discovered 2 laws for circuits that are so simple we don't even realize we're using them most of the time. It's fun to find the voltage and current through every element in a complex circuit. And AC/DC was a band that taught children the types of electric current in circuits back in the 1980s.